Come back. Well, in the first talk earlier this morning, we saw how to count a bunch of things, especially like monomials and lattice points and so on. And now I would like to do kind of the same, play the same game, but right now there's going to be some equivariance thrown into the mix. And by that, I mean that I have some simplicial complex or some polytope and so on, but that also comes with some symmetries. In particular, I want a finite group G to act on the simplicial complex or lattice polytope that you're giving me. And I would like to record basically the same kind of enumerative information we got, but with the extra symmetry in place. So the question, like the motivating question, is basically what can we do if we want to take symmetries into account? So for the rest of the talk, I'm just going to fix a finite group G. And I'm going to work with complex representations. So that everything is nice and I don't get any arithmetic problems. So complex representations. So basically what I want is a group homomorphism from the group G that is given to G, the GL of V, where V is a finite dimensional C vector space. Oh, and before I go on, let me say that what I'm going to talk about, like the new results I'm going to talk about, they come from two different papers. First one is with Emanuele De Lucchi, who's also in the audience online. And the second one is with Akihiro Higashitani from Osaka. Okay, so I'm going to fix this group G, and I'm going to work over the complex numbers throughout. And well, even though I like to think of representations, in this context where the group is finite and the representations are complex, the same amount of information is actually kept by the character of this thing. And that's what I'm going to use from now on. And this is nothing but a map that goes from G to the complex numbers. And to each element, small g, well, rho of G is a matrix. And then I can take the trace of that matrix. And what I'm saying is that if we are in this context, I can retrieve the information about the original representation from the character, which is not always the case if we're not using the complex numbers, but that's good enough for us. Okay, so what's the plan? I would like to substitute numbers. Like earlier on, we had a lot of formal power series, but we're counting something. Like the coefficients were natural numbers. Right now, I want to make a substitution. Instead of using numbers, I want to use characters. So natural numbers should be these characters. They genuinely, like, they are counting something in the sense that they do retain some actual information. But just like before, earlier on, we needed integer numbers to actually have enough agility to move around and do algebraic manipulations and so on. So here, just having characters is not going to be enough. We also need to take stuff like negative characters that wouldn't make any sense from the representation point of view, but we need them as formal object to just be able to basically do the manipulations that we want, which means that I need to introduce a ring which is going to play the same role as the ring of integers. And this ring is what I'm going to call Rg. So what is this? Well, this ring is going to be the ring of complex virtual characters on G. Virtual comes from the fact that I'm taking formal combinations with signs. Complex because we are working over the complex numbers, and well, characters because these are going to be the elements I'm going to see in here. This is actually, like, for people who are more category oriented, this is going to be the same as, it's isomorphic to the Grothendieck ring of representations of the group G. So to us, like for people who haven't heard of that, like, let's just define it. So this thing here, as an abelian group, Rg is free, and the Z basis is given by irreducible characters of and when I say irreducible, I mean that there is no W contained in V such that rho like falls into that. So such that rho G of W is contained into W for any choice of G. Because if that happened, I could actually split my representation into two smaller ones, the direct sum of two smaller ones, and I can only play that game a certain number of times until I hit something that cannot be split even further. Okay, so this is my basis. So I'm going to get a Z basis, which means that I'm going to see stuff like minus a character, and that's exactly the kind of manipulation that I need. And then, well, let me just finish the definition. I'm going to also say, because I'm going to need it later, that an element of Rg, elements of Rg, they are virtual characters, they kind of correspond to integers. So I would like to say, well, who are the natural numbers in here? Who are the things that actually count something? It's the usual characters. But such elements are going to be called, effective. If all coefficients with respect to the Z basis I gave you, all coefficients are non-negative. And this is exactly the same as saying that this object, that in principle it's a virtual character, is actually a genuine character. So it could be interpreted as the character of an actual representation. So this is how it works on the level of abelian groups. How do you multiply things together? How do you sum them? Well, sum and multiplication are going to be induced by the rules that we get for actual characters. Multiplication. So, sorry, I'm going to write it here. If I have two actual characters, the sum is going to correspond to the character of the representation that I get by taking a direct sum. And as for the product, I'm going to have the character corresponding to the tensor product of representations. So on the matrix level, here I'm just putting things together like in a block fashion, and here I'm taking a Kronecker product. Okay, so if these are the rules, and then you can just extend in the usual way so that also negative elements behave with respect according to this kind of rule. So you get a ring. This ring is called Rg, and that is going to be the ring of coefficients for all the structures I'm going to introduce now. And let's do an example before we go into the questions. So let's say this is the example I'm going to need the most. If I just take Z2, there are only two reducible representations. One of them is the trivial one, which I'm just going to call it the trivial one for now. And the sign representation. So what's the definition? This one is just going to be defined as whatever I do, I just get 1 in response. Whereas for the sign representation, I'm just going to get 1 when G is 0 and -1 if G is 1. In this case, both things are one-dimensional representations, so I don't really need to distinguish between the representation and the character. In general, I could get something of which I need to take the trace. So these are my objects. And now it's like, OK, we do have one. This thing is going to be the multiplicative neutral element, because like when I multiply things together, when I take the tensor product, it's not going to do anything. And now I need to know what the sign does when I multiply it by itself. So in this case, who is this element? So if I do this, I just need to multiply the values. So I'm going to get 1 times 1. So that's 1. But that's also the case when I do chi of the sign representation evaluated in 1 times itself, because this would be -1 squared, which means that this representation, when I evaluate it at 0, gives me 1. When I evaluate it at 1, also gives me 1. That means that this relation holds. This is the one, like the one given by the trivial representation. And that's the only relation I'm going to see. This implies that the ring I'm interested in is just C of chi sine modulo the relation chi sine squared equals to 1. And more generally, if you want the cyclic group here, you're going to get something like that. You're going to get C of a certain representation chi modulo chi to the n minus 1. OK. What time is it? Yeah. Let's make a slightly more involved example so that you see that, I mean, this ring is kind of too nice in a sense. Things are going to be more complicated in general. If I take G to be S3, the symmetric group of 3 elements, there are 3, sorry, I'm just going to give you the table of representations. These are going to be in one-to-one correspondence with Young diagrams. And I can evaluate them at conjugation classes. What I'm going to get, this is the trivial representation. No matter what I do, I get a 1. This is the sign representation. It reads the sign of the associated permutation. So I'm going to get 1, -1, 1. And that is like the one that is not so clear. It's called the standard representation. I'm not going to go into that. But let's just say that whatever it is, when I evaluate it at the identity, I get a 2, which means that this object is 2-dimensional. I get a 0 for transposition. I get a -1 for cycles. So that's the whole information I need. And to form the ring, I also need to know what happens when I multiply this element by itself, this element by itself, and these two together. And it turns out that if you do this, you get, again, 1. If you do this, you get back the second element. And if you do this one squared, you get the sum of the 3 of them. I'm not going to go into that. It's just that, kind of like I did for that case, one needs more patience, but you can actually find these relations. And if you put things together, it means that R of S3 is Z of AB modulo the relations A squared equals 1, AB equals B, and B squared is 1 minus, well, B squared would be 1 plus A plus B. So I get that thing. And that's kind of what you know. As you see, it's not the nicest ring to look at, but you do get some structure. Yes. Oh, sorry. It's my bad. This one is supposed to be a Z. Thanks. Thank you. Yeah. This one, well, the representation is two-dimensional. Yes. Okay, so it's two-dimensional, and I get something that, yeah, exactly, 1, 1, and 2, right?
I can see, yes.
Yeah, no. It's very likely that I'm gonna make mistakes when I do this, so just please, yeah, catch me then. Okay, other questions? Okay, so this is my, well, now we know what numbers are in this context, and we want to use these like elements in here as the new coefficients for our like equivariant Hilbert series or Ehrhart series and so on. So let's go into that and let's see what happens for simplicial complexes. Okay, so I need my group G to give me some symmetries of the complex. So I need G to act on sigma by simplicial automorphisms. I need, well, the right concept of invertible morphisms. So yeah, which means that you get something from the vertices to themselves, which is a bijection. And whenever you get a face by going the other side, it means that you came from another face. Whatever it is, it's like it's the right way of thinking of invertible maps for simplicial complexes. And then if I do this, because of this condition, the faces of sigma are just going to be permuted around. And so remember that the standard Riesner ring is nice from the graded structure point of view, because like its graded structure is kind of guided by how the faces behave, which means that not just the faces of sigma are going to be permuted, but also the monomials of the standard Riesner ring are just going to be moved around by this action in a degree preserving fashion. I'm saying a degree preserving fashion because I would like things of degree 3 to stay within the same degree. Otherwise, like my graded structure is just going to go all over the place. Which means that I get an induced action on each set of monomials. Now, remember from last talk that the Hilbert series of sigma, of well, C of sigma, was just 1 plus the basically how many monomials there were in each degree. So right now, I have more information. I also know how many there are, but I know how they're moved around by the action. So what we are going to do, well, this thing is going to give me a character. Well, this thing is going to give me a character. according to how these objects are shuffled around. And then if I want to do the equivariant version with respect to this action of sigma, again, I'm going to put a 1 just because this would be the empty phase. And by convention, I just want that to stay in place. And from then on, I get the character of the action on the monomials times t to the I. Now, what is this thing? Well, it's a series, but the coefficients are elements in Rg. So this is a series, but it's not anymore a series with natural coefficients. It's a series with effective characters as coefficients. So I'm putting a plus here just to remember that up to now, these are genuine characters. They are not virtual. They are really counting something. Well, they're taking care of the action on the monomials. Okay, so we might do the same also for faces. So we can introduce this would like to be a Gothic F. I'm never going to be able to do that. But Fi, well, Fi minus 1 probably.
Okay, so what is the plus mean on the RV?
Where? Yeah. Oh, yeah. I mean that, well, Rg is made of virtual characters, so they would be formal elements. But at the moment, this thing is a genuine character because it really does something on the monomials. So this object would be a positive combination of irreducibles. Thanks. So right now, because of monomials are permuted, but so are faces. So I can actually say, well, I'm just going to take the I-dimensional cardinality I faces, I minus 1 dimensional faces, and I'm going to remember how the permutation shuffles them around. So I'm going to get another character. And then I can define some kind of Gothic H. This one, well, I can write it down, but very quickly. It's the same formula as before. It's just that instead of shuffling around numbers, these are numbers so far, but now I'm going to put the equivariant version here. So this object is again effective. This one, well, in general, is going to be an element of Rg, but it's not necessarily effective, just the same way as this used to be an integer, but not necessarily a natural number. Okay, so what? Well, we know what comes next, right? Because we know that in the standard case, the classical case, if you want to access the Hilbert series, you just go check the phase vector and see what happens. So it would be nice if K is just a number in 0. D. Yeah, it's the U, sorry, D plus 1. Yeah. The only thing that has changed with respect to the previous formula is that this thing is now this guy here and not a number anymore. Yes. Well, rho is used in the fact that this character, like the monomials, are permuted according to how rho acts. So I would like to, formally, I need to remember that this is equivariant with respect to that specific action and not just any. Thanks. Good question. And so one might hope that the equivariant series that I've just defined equals, well, what we did before, right? We had Fi minus 1, I that goes from here to here, t to the I, 1 minus t to the I. That seems like a reasonable thing to ask for. However, that's not quite right. Not in this level of generality, at least. And I'm just going to give you a counterexample. Don't want to go over time, though. Yeah. So if you want an example where this does not work, just think of this. Just take a segment and act on the segment by just swapping x and y. So what's weird here? Well, the not so nice thing is that x goes into y goes into x, but the segment xy stays fixed, which means that if I'm just going to consider all the elements that are fixed by the element 1 in Z2, that's not a simplicial complex because xy is fixed, but x is not, which means that for this particular action, so these would be the faces of sigma such that this holds. So the elements in sigma that are fixed by this thing, this is not a simplicial complex because xy lies in here, x does not. This is exactly what messes up this equality. Because in this case, if you were to compute this and that separately, they would both make sense, but they would not agree. And I'm not going to go into the details because I don't think we have enough time, but one can show that just by going and saying, okay, if I take the monomials, I'm going to take, say, x squared, xy, y squared, and two of them get swapped, one of them stays in place, and you can actually get the expression of the character from there and so on. And if you do that, you're going to notice that you don't get equality. Let me stop for a second. Yeah. Yes. Good observation. Yes. Actually, even like if you take any group and you evaluate your expression at the identity element, well, nothing is being done, which means that you get back all the classical things that we defined so far. And actually, you can get even more than that. So, other questions, sorry. Okay, awesome. So that's always true. But in general, so far, it's not so clear why this thing should be remembering symmetries somehow. And, in that generality is not quite true. But if I give you something more for the action, and I think this is like, I'm just going to attribute that to Stambridge because there is a paper of his where he does exactly that. I'm going to say that rho is a proper action if that kind of behavior that I've just described never happens. So whenever G sigma is the same as sigma, it also holds that G tau is the same as tau for every subphase. And that's not the case in the example I have here. Yes. Sorry, this one.
Yeah, no.
Oh, yeah, this simplicial complex. So you get just C of xy as your standard reason ring. Okay. So why do we care about this kind of action? Well, if rho is proper, then, well, that equality now holds. So great, that's something that we have recovered. And then I get something nice about like remembering symmetries. What is that? Well, if you do evaluate your object, so this is a thing where each coefficient is an element in Rg. So you can evaluate that at G. What you're going to get is the Hilbert series Of whom? Well, of the object that is fixed by the element G. And notice that, well, to be correct, I guess I should write this. Yeah. Notice that this thing is now a simplicial complex, just because that's exactly what this condition is saying. So now it makes sense to consider this as Stanley-Reisner ring. It has a Hilbert series, and it happens to equal what you get when you evaluate the big object at G. So in this sense, the equivariant object remembers both the standard thing and all the G fixed stuff at once. Yes? Sorry, say it again.
Like instead of taking help of a fixed sub complex, I guess with a fixed sub ring, then I would need proper.
That could be. I think we should discuss that later, because it's like these things are kind of, subtle. So I'm not gonna say yes, but it's likely. Other questions? Yeah.
What are the pools in the case when it's proper?
Mhm.
The F I minus one are the one with sigma or the one defined this morning?
Where is that? Like here?
With the formula there.
Yeah, this is the same. I forgot
Oh,
the sigma.
no.
Yeah. I mean, it's just that I'm trying to write it as a Gothic F, but with
Okay.
very poor results. Okay, so that is nice. That's something that we do recover, but we're not quite there yet, in a sense. I mean, properness is nice in the sense that we do get something which is genuinely equivariant in this sense. We recover symmetries and so on, but there are still some things that kind of don't work the way we would like them to. So for instance, take this example. I'm just gonna take an empty triangle, and I'm gonna act by Z3, and Z3 just moves vertices in a cyclic way. This action is proper because, well, basically nothing at all is fixed aside from the empty face. So this thing is proper. If you try to check for this, it basically never happens if not for the empty face, because everything gets moved around. This object is gives me a Cohen-Macaulay complex. So this sigma. Sigma is Cohen-Macaulay, rho is proper. So we would like to find an expression that gives me, well, the H, the H numerator, so the equivariant H vector, if you wish, should be made of effective objects if we were doing things the right way. Because when I'm starting from something Cohen-Macaulay, so the original one has a positive H vector. I'm quotienting by something that kind of respects the symmetric complex structure. I would like to get something that is effective. However, if you do the computation, so we do know that we can get it that way, so by the usual business. But it turns out that this object here is not effective. So somehow properness alone is not quite enough to give us what we'd like. So we need another strengthening. Okay. Yeah, doors open. Okay, so I would like to find a strengthening of that property of properness that is gonna give me effectiveness when I deal with the Cohen-Macaulay complexes, and I just go modulo. Well, I consider an action with these nicer and stronger property. And this happens to be what we called, well, Emanuele, I think, was mostly responsible for his name. The name comes from hyperplane arrangements and infinite periodic hyperplane arrangements. Whence the name, which could be a little strange in this context, of translative. So not transitive, translative, different. And what is the actual condition? It's even stronger than properness. It says that in this context, if you do have, say, V and GV, so V is a vertex, GV is a translate of that vertex. If this thing happens to be a face, well, then it's better that these two things are actually the same element. And let's go check a case where this does not happen. It's exactly this example here. Here, even though I do get something proper, this vertex gets mapped into this other vertex, and these are connected by an edge of the complex. So that violates that condition. And you do get, in general, that translative is stronger than properness. Translativity is stronger than properness. You can sometimes come back, and this happens when the exponent of the group is 2. So if you're looking for a counterexample with Z2, you're not going to find it, because in that case, things are equivalent. OK. So what's so nice about translativity?
Sorry, can you?
Well, the idea here is that there is a feature of this whole rational expression business that is kind of unique to, I mean, it's not unique, but it's something new that arises from this context. Usually, like when you have a Cohen-Macaulay ring, you just get any linear system of parameters, you go modulo that, and you're going to get, well, the H vector of the Artinian reduction is the same as the one you originally had. However, in this context, first of all, you need to choose a linear system of parameters that is G invariant. Otherwise, you're going to destroy the structure. But even so, different choices of linear system of parameters are going to give you different rational expressions, because the denominator is also containing part of the information. And that, why am I saying this? Because being translative is pretty much the same, even though it doesn't look like that from this definition, is the same as having a linear system of parameters that is transparent with respect to the action. Basically, I get a linear system of parameters where each single element is in the subgroup that is fixed by the group G. Let me write it down. So rho is translative.
Hello, can you hear me?
Here, I'm actually assuming that sigma is Cohen-Macaulay. So if C of sigma has a linear system of parameters, theta 0, theta d, such that G theta I is theta I for any G for any I. In other words, every single element here lives in RG, in the sense, sorry, not that RG, RG on top. So the part of the ring C of sigma that is fixed by the group, the invariant ring of C sigma. And there is also a combinatorial characterization that I'm just going to mention, because that opens the way to the multigraded world, like John would like to, for instance. The combinatorial version is that rho is translative if and only if there exists a proper coloring of my complex. So I'm basically coloring the vertices so that no monochromatic edges arise. Yeah. That is preserved by the action. Notice that here it's something weird that happens. The definition I gave you does not use colorings at all. However, it turns out to be equivalent to the existence of some proper coloring that does the trick. I'm not telling you which one it is. I'm just telling you that some exists. So it's kind of, there's kind of, I could be doing everything in the multigraded setting, but not everything would go through so smoothly. Well, because now you don't exactly know which coloring you're using. You don't know exactly which multigraded structure you have. So what is the takeaway? Takeaway is that if sigma is Cohen-Macaulay and rho is transitive, then you get what you want. You get that HI is effective for any. Good. Any questions? I know it's quite a lot, but yes. Mm-hmm. Oh, that's just a finite set. I didn't want. Yeah. Let's say. I mean that vertices of a certain color are just going to be moved to color vertices of the same color by every element of G. Yes. Yeah. And by the way, that means that you can take a linear system of parameters that is going to be colored and G invariant. So you can just group together things of the same color. If your coloring is also balanced, then it's the nicest possible situation because you can just go collect vertices of the same color and go modulo that. But even if you have more colors than you would like to, you can still work your way around that, and it still works. Okay. So that's one part of the story. I don't want to go over time, so I'm just going to give you a kind of short version of the rest. We did what it means. Well, we showed what it means to have an equivariant Hilbert series for a simplicial complex. We can do the same for polytopes and find an equivariant version of the Ehrhart series. Here, well, the setting itself is a bit cumbersome. I don't really want to go much into that. But let me just say that if you do have a polytope sitting in a lattice, and I'm acting by affine transformations that keep the lattice in place and the polytope in place, then you can just think of, well, all the lattice points, they are just going to be moved around, just like the monomials did for this case. So under the right hypothesis, you can define this, where P is a lattice polytope. And it's going to be, well, again, instead of counting lattice points, now you're just going to have a character of a permutation. So you take the polytope, you dilate it, you see who the lattice points are, and you see how they are going to be permuted, and you retain this information. So again, this thing is a formal series, and the coefficients are effective. Now, what's the problem? Well, first of all, I have to say that this setup is due to Alan Stapledon, who did that in 2011. And the main difference with the case of simplicial complexes is that here you do have a right denominator to choose. And in this case, so you can define the H star vector of this thing, the equivariant one. In the usual setting is just the Ehrhart series times 1 minus d to the d plus 1, so they do cancel denominators. Here, you have to be more careful because you also want the denominator to remember how the lattice changes. And it turns out that the right thing to do, which I'm not going to go into, is considering this strange object, whatever this is. This thing is a polynomial that I'm not going to define, but it kind of takes care of how each level changes. Each level, I mean each environment changes at each height. And this thing is a series. This thing is a polynomial. This object is not necessarily a polynomial in this context. It's just a series, which is, again, a difference when compared to the usual case where this was just the numerator of the rational expression you got. And I would like to mention that it's not so clear when this happens to be a polynomial. It's still a conjecture. It is conjecture that whenever you do this construction, you see the coefficients that arise here because this thing is a series, and you only find effective coefficients all the way through. This happens if and only if you actually do get a polynomial. Effective implies polynomial is not so clear that the other direction holds. And yeah, so it is known to hold when the polytope has a triangulation that is G-invariant, which is the case that we are interested in mostly. Okay, so we would like to have some kind of equivariant version of a Bethke-McMullen theorem. Which means that I would like to say, hey, if I have a polytope and I have a triangulation that is actually fixed by the G action, well, I would like the equivariant Ehrhart series and the equivariant Hilbert series to coincide just in the in the usual case. And that actually happens if you're interested at, if you're happy with doing that on the level of series and not of rational expressions. So I'm just going to have it as a theorem. So if P has an G-invariant unimodular lattice triangulation, so the complex is preserved, maybe not pointwise, but is preserved as a whole, then and I'm going to attribute this to Yochemko, Katten, and Reiner because they had it in some unpublished notes that they kindly let us use, but unbeknownst to us. So we actually found out after the first version of this paper. So this is I'm just going to say that this works on the level of series. If you want something nice on the level of rational expressions, you need to ask for more. So if furthermore rho is transitive, then you get the expression you'd like. Let me call it. Okay. And each single HI is effective. Notice, however, that this is not quite the right denominator to have, in the sense that if I do want that's why I didn't call that the H star polynomial, because this would be the H star polynomial, and that's not quite that. You need to multiply by this and divide by 1 minus t to whatever. So you need you can extract this thing from that, so that's a genuine way to get the H star vector, but you're not going to get some of the nice features like being palindromic and so on. And yeah, I'm going to show you an example, which is the one we had before. Remember the hexagon we had this morning? Well, we can actually act on this thing. Well, this is going to be a unimodular triangulation, and I'm just going to consider the action that reflects everything along this diagonal, like this. If you were to do the computations, you could say, okay, well, the empty set stays in place. So what happens to vertices? Well, these three vertices stay fixed. This one gets mapped to that, and this one gets mapped to that. So you have three fixed things and two pairs, and that translates, believe me on this, to having this amount. So this is gonna give me the fixed things, and this is gonna tell me how many pairs get swapped. So overall, we get this. I'm acting with Z2. Then for edges, 1 and 2 are fixed. The other 10 are subdivided into 5 pairs. And as for triangles, 3 pairs get swapped. If I do Stanley's trick, this time in this equivariant way, still works. Which means that the equivariant error series of this object here is indeed made, like, has a numerator that is indeed made of positive pieces, effective pieces. And you could do a multi-graded version of all of this using colorings. That works, and it works especially well when the coloring is balanced, but of course I don't want to go into that. Yeah, and I'm about to finish, so I'm not going to use the rest of this, don't worry. I just want to say something. This is one of the results we had. In general, one of the reasons why I'm saying that this is the right expression for the H star vector is that, for instance, you do get a palindromic version of this exactly when you expected that to happen. So basically, when your polytope is reflexive, well, this thing might not be a polynomial, but as long as it is, then it's going to be palindromic as well in this extended sense, which means that you can compute the equivariant gamma polynomial. And in some cases, this thing is going to be made of positive characters. And the result we have with Akihiro, which I'm not going to mention right now, is that for order polytopes, so a particularly nice and well-studied class of polytopes that arises from posets, well, if you take a graded poset, then your object is known to be reflexive, I guess, which means that, or in any case, Gorenstein. So the numerator, the H star vector, is going to be palindromic. It is going to be palindromic also in this sense. And it turns out that it is also gamma effective. And the proof uses a lot of machinery, which is very much combinatorial in nature. It uses some concept defined by Branden about sign graded posets. So if you're interested in combinatorics, just come and ask me later. Thank you so much for your attention. Yep.
So knowing that rho is translated in binary about the equivariant.
Yeah, well, I'm not really expert about toric geometry and the like, but the paper by Stambridge, this paper here, was actually doing exactly that. Like, if you check the original paper by Stapledon, there is a section where it actually says that what Stambridge was doing and other people were doing was basically just the same scenario that you get on this side. And that's another reason why this is the right denominator to use, because if you do use that, you get exactly that you're describing how the action works on the polytope in the toric variety sense. Tors? Oh, sorry, my bad. So for Tor modules, I guess so. I mean, like, I do think that this should also translate to more information about the resolution and the Betty numbers. I know there is a paper by, well, two papers, one by Raiku and one by Raiku and Murai, where they do resolutions of monomials, monomial ideas that are Fn invariant. I think, but I don't quote me on this, but I seem to remember Claudio saying that the equivariant information was more into the X part than it was in the Tor. So that's what they use to prove the result. But yeah, in general, I would say that some of this is going to translate also to finer invariance.
So you have the generalized F vector,
Mhm.
right? But for regular F vector, you have like I don't know if the same question is intense, but can there be any sort of example?
I don't know. Just, well, fact is, the Kruskal-Katonat result was something in terms of like expressing the things in terms of certain binomial expressions. I mean, since these are not numbers anymore, I'm not sure what the corresponding right thing to do would be. But it, you know, may depending on how you ask the question, you might actually get a meaningful answer.
It should have something to do with. One way you can read the binomial coefficient is you're writing a K class as a sum of K classes of projective spaces.
Okay.
So maybe the right thing to look at would be the equivariant K theory of the, with respect to the group action of, you know, wherever this is being embedded with this action.
I
There's some
don't know it all, but
action where this torque guy is being embedded, and I think it would have to do with expressing the class of the subvariety as an equivariant K theory for that guy where the equivariance is supposed to.
Yeah, I don't know if anyone has done that. I mean, like, that sounds cool. I don't really know anything about equivariant K theory, so I'm not gonna say that I understand exactly what's going on, but I think that no one has done that in the literature, at least in my, not to my knowledge. Yeah.
About order polytopes. Are you saying that they only, the results only hold in the graded case?
Well, fact is, for order polytopes, I mean, I said that briefly, I didn't really write it down, but as I said, this thing is usually a series and not a polynomial. But when you do have a G-invariant lattice triangulation, Stapledon proved recently in a preprint that you do get effectiveness, and hence this thing is also going to be an actual polynomial. So order polytopes, any order polytope, I mean, if you have a poset P and you act by automorphisms of the poset, then you're going to get an induced action that basically swaps, like permutes the coordinates of the ring, of the affine space you live in, and that is going to give you an induced action. That thing, well, in any case, you're always going to get a G-invariant lattice triangulation. That is the one that comes with like filters of the poset or order ideals of the poset, like the standard one by Stanley. That one is going to be G-invariant, so that's good enough so that this thing is a polynomial. However, if you want this thing to be a palindromic polynomial, also in the classical sense, you need your poset to be graded, and that's a result by Hibby.
Another question, speaker.